All right, so today we're going to discuss a battery-free Game Boy done by a group of researchers at Delft University of Technology and Northwestern University. And just as a disclaimer, I did not work with them, and I am simply presenting their research. So before we jump in, here's a brief overview of what we will discuss. First, we will do an introduction on the battery-free Game Boy and discuss what it is and why it's important. Second, we're going to identify some challenges they immediately saw when tackling this problem. Third, we will discuss the design decisions that were made to address and mitigate those challenges. Fourth, we will discuss how those design decisions were practically implemented. Fifth, we will discuss how their design did. And lastly, we will discuss the future work and improvements they would like to do moving forward. All right, so on with the introduction. So why even move towards battery-free gaming? So there are three reasons. The first one is batteries add size, weight, bulk, cost, and inconvenience of charging to any device. So think of a phone today. It's a good chance that more than half the size of your phone is from the battery. And wouldn't it be nicer if you didn't have to recharge it each day? And it cost less and it weighed less. That's what they're trying to do here, just in Game Boy format. Second, batteries have a very large negative impact on the environment, so reducing the need for batteries in the gaming industry would significantly decrease the impact of devices on the world. Third, there's a precedence for working prototypes of other battery-free devices. So battery-free technology has been used to make phone calls, deploy machine learning on their greenhouses, stream videos, and much, much more. And this paper hoped to push the bounds of battery-free devices to include interactive battery-free devices as well. So in order for battery-free gaming to be feasible, intermittent computing had to be proven first. So intermittent computing is the act of doing calculations in between periods of the device being on and off without losing its progress when it's turned off. So the reason the device is expected to turn off is because intermittent computing is normally paired with energy harvesting. And energy harvesting is using the energy from around you to power devices. So energy can come from environmental factors like wind or solar energy, or from the device itself, like mechanical energy of buttons being pressed. And so, as you can see in the image here, the battery-free Game Boy builds off this technology and uses sunlight and button presses to replace the battery in the system. The gray areas represent times when the device is off, and then right before this off state, the state of the device has to be stored. And then once enough energy is gained to run again, it turns back on, restores the state, and continues operation as normal. Energy gathered from the button presses helps to prolong the on time of the device, and we will discuss this more shortly. All right, so now on to the challenges that the researchers identified for the research. The challenges are motivated by building the foundations of a battery-free mobile gaming device to increase convenience for users and provide an environmentally sustainable device. All right, so the first challenge, as we already discussed, is energy harvesting. So energy harvesting is unpredictable due to uncertain environmental conditions. When you travel, you move from sun to shade or varying distances from radio towers, which are all sources of ambient energy that can be drawn from to power your device. The second challenge is keeping track of game state. There are frameworks out there that support intermittent computing by saving state to FRAM before power down, but most of them will trade memory efficiently for performance, which isn't acceptable in gaming because memory efficiency is needed to run a game effectively. The third challenge is the enormous variety in games. Games can vary in memory size, number of actions, difficulty, and number of button presses. So developing a model that will work for most games will be very difficult. The fourth challenge is a game's high computational load. So games run on highly efficient platforms, and all intermittent testing has been done on a small, tiny NSP430. The fifth challenge is capturing user actions. The battery-free Game Boy will depend on button presses to gather energy to keep the device running longer. The use of continuous button pressing and screen refreshing has not been seen before in interactive battery-free devices. And then the final challenge is a realistic demonstration. The goal is to play a real, unmodified game and keep the user experience as positive as possible. And with all this new technology, it may be difficult to do that. Right, so now we're going to discuss how challenges were addressed in the design of the battery-free Game Boy. So before we dive in, we're going to go over how this Game Boy was modified to do everything it needs to do. Modifications can be broken up into hardware designs and kernel designs. The hardware consists of mechanical energy harvesting buttons, a display, a slot for Game Boy cartridges, and energy harvesting circuitry, which is where the solar and mechanical energy is stored in a small capacitor. The kernel consists of a patching and checkpointing system to handle saving and restoring states, as well as the Game Boy emulator. Alright, so the key ideas to making the Game Boy work is gathering energy from gaming actions in the environment, tracking the checkpoints, tracking and checkpointing the minimal state at system level, using processor emulation to play games, and speeding up intermittent computing. So, as mentioned before, the Game Boy will harvest energy from sunlight and button presses. Using both an environmental and a mechanical system for harvesting energy allows flexibility in playing locations and helps overcome the unpredictability of environmental factors. Next, the system will handle large amounts of memory by checkpointing only the memory that has changed since the last time. This helps increase performance and reduce computational load. Next, the system will use an emulator to run games. This allows the researchers to focus on the intermittent computing aspect of the device, as well as allow the device to run thousands of different types of games. This will help mimic the real world better. And then finally, speeding up intermittent computing is a must. The researchers chose to go with the ARM Cortex microcontroller and external FRAM to speed up computation rather than stick with a traditional MSP430. So as mentioned, a Game Boy emulator is used to run the games. The emulator works by reading instructions and executing them in native code, trying to mimic the emulated CPU as closely as possible. As with all games, the emulator requires the Game Boy input-output to run the game. So since the researchers are collecting energy from buttons, they have to modify the emulator to disallow the holding of buttons. So in Super Mario, say, to move right, you have to keep pressing the right button instead of holding the right button. And so this ensures that the user keeps pressing buttons in order for the system to keep collecting energy. Notably, this does increase user experience. This decreases user experience. Additionally, the original Nintendo Game Boy does not have an FRAM buffer, so if power is lost, the screen cannot be restored. Thus, an FRAM buffer was implemented in order for it to be saved and restored. Alright, next is checkpointing. So checkpointing is used to handle power failures during gameplay. However, checkpointing usually saves the entire system state. And with a system that is supposed to be as responsive as possible, checkpointing needs to be a lightweight solution. Thus, the researchers decided on a method that checkpoints only the parts of the device memory that was changed since the last checkpoint. In the figure above, you can see some preliminary testing that showed that this idea was feasible. So you can see the darker sections showing the memory that was rarely touched during game execution. So this is classified as differential checkpointing. Checkpointing can also be categorized into corruptible and incorruptible checkpoints. So corruptible checkpoints use the same location in non-volatile memory for checkpoints, and this reduces non-volatile memory requirements and runtime development. However, if the previous checkpoint doesn't complete, parts of the checkpoint may be overwritten with the current checkpoint, and this requires exact prediction of energy, which is not possible for intermittent computing. So the incorruptible checkpoints were decided upon. It's a system that guarantees that there is always a valid checkpoint that can be restored, and this system relies on the use of double buffers. Notably, the energy supplying capacitor is monitored, and checkpoints are only taken when the device is nearing power failure as well. All right, so for patching, patching stems from all these checkpointing needs. So patches are non-volatile copies of consecutive volatile memory that are modified since the last checkpoint. Since multiple memory regions might be modified during execution, multiple patches may be used to complete a single checkpoint. There are 3 operations related to patching, which is patch stage, patch commit, and patch restore. In patch stage, a patch is created, so non-volatile memory is allocated, the modified volatile memory is copied, and then the patch has the logical clock value added to the front of the patch chain. And just a couple of definitions, the logical clock tells the system which buffer to use for restoration, and the patch chain is a list of patches to be applied during restoration. Okay, so the next operation is patch commit. So in patch commit, the logical clock gets incremented, telling the system to look at the newly staged and now committed patches for restoration. So in the figure on top, you can see the new staged patches in red and the committed patches in blue. So currently, if a restore happens, the n-1 patches will be restored. However, once n is incremented to n+1, the patches tagged with n will be the patches first up for restoration. Alright, so finally, in patch restore, the newest patches are copied into memory, followed by the later patches. If patches overlap, the overlap from the older patch is ignored. So in the bottom figure, you can see if on the left, a device that was turned on after being turned off. And then on the right, you can see the order in which the patches were applied in memory, with checkpoint 3 being the newest checkpoint and checkpoint 1 being the oldest. All right, and now we go on to the real-world implementation. So significant consideration was made when selecting the components to make the batteryless Game Boy. So you can see the board design depicted here. Notably, an ARM MCU architecture was selected and external FRAM was applied. The buttons were dedicated energy harvesting switches that generate energy by moving a magnet inside a coil on each button press. An ultra-low power LCD display was selected for its low energy consumption, and other considerations or other modifications were made, like removing the sound outlet, adding solar panels, adding a USB port for debugging, and some other aspects. All right, so on to the emulator. So the emulator was not custom made, as there were already emulators out there. As mentioned before, changes to the emulator had to be made to modify button handling and screen saving. And notably, the button holds were limited to 300 milliseconds, and the memory configuration of the device can be seen here. So, as you can see, Flash holds the MPatch and emulator code, as well as the non-volatile game data copied from the game cartridge. SRAM contains memory of the entire Game Boy and the volatile game memory or game data. FRAM contains the 2 buffers for checkpointing and all created patches. Then an additional modification to the emulator is that the screen allowed for color display, so colors were remapped from grayscale to color. Alright, so as we mentioned before, MPatch is built upon a double buffered checkpoint scheme, and you can see the algorithm here. So first, MPatch will checkpoint all the emulation management logic except for the emulated game memory, as the game memory is checkpointed using patches. Then patches and checkpoints of the emulated game memory are created. Notably, initial memory modifications are tracked using the memory protection unit of the MCU. So when a region of emulated game memory is written, the memory protection unit triggers and the memory region is marked as modified. So this is how the system knows where to create patches from. And now here you can see a little bit more of the 3 stages of patching. So the patches are a little more complicated than previously explained. Along with the copy of the volatile memory region, a patch has metadata that contains the value of the logical clock, the interval of the volatile memory, the next patch in the chain, and the metadata to build an augmented interval tree to speed up restoration. The patch sizes are allowed to differ with the complexity of dynamic allocation in embedded systems. Multiple fixed-sized blocks can be allocated. Uh, yeah, multiple fixed-sized blocks can be allocated and chained together to create enough space for the patches. And then data restoration starts with discarding all staged but not yet committed patches. And then, as mentioned before, the patches are iterated through, grabbing only the sections of memory that have not been restored by any patch. And to keep track of the parts of memory that have already been restored, an interval tree is kept. So when the patch is applied, its range is added to the tree. And when the next patch is applied, the range is checked in the interval tree to see if it has already been updated. If it has, the memory section is split and the part that has not been applied yet is applied. So if a patch has been identified that it does not need to be used anymore or it's not useful, then it will be deleted. And to do this, it is simply freed and then deleted. All right, so now on to evaluation. The battery Game Boy did evaluations of different lighting, the power consumption, and the M-Patch system's performance. All right, so for lighting performance, Tetris was chosen as the game used to evaluate performance across different lighting scenarios. So in this experiment, Tetris was played without limitations, once in daylight and once in shade, and the main supply capacitor and other debugging signals were recorded. So in the figure above, the green, or the dark green, represents initialization, the light green represents system on time, the light blue represents a low energy state, which is where checkpointing starts happening, and the dark blue represents checkpoint time. Additionally, the light blue dots on the wave mark button presses. So in the top figure, which is daylight, you can see that 10 or more seconds of on time was recorded with off times of less than a second. And in the bottom figure, which is shade, you can see that 3.5 seconds of on time was recorded with more than a second of off time. All right, the second test was power consumption. So taking an average over 10 seconds, the MCU and the FRAM combined consumed approximately 11 milliwatts, and the screen consumes approximately 350 microwatts of power during game execution. So in total, the system consumes about 11.5 milliwatts of power compared to the 132 milliwatts of the original Nintendo Game Boy. Additionally, the power provided by the buttons and the solar panels were recorded, and the buttons registered about 2/3 of a millijoule per press per second, and then the solar panels recorded approximately 10 milliwatts in daylight and 8.3 milliwatts in the shade. So combining the buttons and the solar panel, it is less than the 11.5 milliwatts the Game Boy consumes, which contributes to the off times that are seen when playing the game. All right, so the final evaluation of the evaluation was the M-Patch system. M-Patch was compared against all active memory in a system being copied to non-volatile memory during checkpointing, regardless if it was modified or not. So checkpointing was compared across 4 games: Tetris, Super Mario Land, Space Invaders, and Bomberman. So to do the checkpoint, the systems were run on constant power and perform a checkpoint every C cycles of the emulator instead of using the intermittent computing capabilities. So the top image shows the cost of the core checkpoint is about 30% of that of the completely naive checkpoint, with the rest of the checkpoint time coming from creating patches of emulated memory. So thus, MPatch is more than 2 times faster than a naive approach. And then in the bottom figure, you can see the results of the restoration time of MPatch checkpointing. Notably, restoring a checkpoint takes more time than creating a patch, thus large improvements aren't seen. That being said, MPatch still often reduces the restoration time compared to the naive approach. All right, and now we're going to detail some of the limitations of researchers identified in their own work and things they might consider doing in the future. Right. So despite all of the work that the researchers have done, there are still significant limitations of the battery-free Game Boy. The first limitation is that sound was not implemented on this Game Boy, so this is one aspect that makes the Game Boy not yet fully immersive, but the lack of sound is due to the fact that making sound enjoyable while having intermittent power loss is still an area that needs to be researched. It's not really enjoyable to like listen to. And then the second limitation is playing in the dark. The buttons do not produce enough energy to power the device themselves. Additionally, a better backlit screen is needed for the user to see what is occurring. Though a backlit screen is not very practical as it draws more energy from an already resource constrained system. The third limitation is haptics. The buttons used are more sturdy than those of a normal Game Boy because they have to withstand frequent button presses. Additionally, aesthetics of the device are reduced due to the placement of the solar panels, and these will be improved over time as parts of intermittent computing become available. Right, so the fourth limitation is networking. The original Game Boy allowed you to connect to another Game Boy via cable to play games together. A future idea is to use this cable connection to share energy between the two devices. The fifth limitation is consistent playability. Off times are a big factor in what games can be played on the battery-free Game Boy, and games with minimal off time will cause little irritation to players rather than those with larger off times. Additionally, games with minimal button presses will be more pleasing to play, but that contradicts using button presses to generate energy. Finally, the last limitation is screen retention. Currently, the screen state is not saved in between on states, so implementing the screen save state would reduce the perception or perceived effect of intermittent computing. All right, and that with that, that is the end of the presentation. So thank you for watching.